In this video, I would like to introduce some of the techniques used by people in the industry to do graphics. Meet Bart the Bug. He's currently centered at the position x equals 0. He lives on that line. He is one-dimensional. If I want to flip him over, I just have to, like that, I just have to multiply him, all his points, by -1. But if I want to move him from side to side, I would have to add. And I can't add to points and it still be a linear transformation. For it to be a linear transformation, I'm going to have to embed Bart the Bug into 2-space. So that's what I'm going to do. Now he lives on the line y equals 1. His position will always be a comma 1 to a plus 2 comma 1 because he's 2 units wide. He is currently centered at position 3, 1. So let's say I want to move him. To do this, I need to represent him as a matrix. So let's represent him as 2, 1, 4, 1, or 2, 4, 1, 1, however we say it. So each column represents a point on Bart. One is his left side, one is his right side. And I want to figure out what matrix to multiply him by to move him. So let's say I'm going to move him 2 units to the right. So his ending position is going to be 4, 6, 1, 1. Now, looking at this, I want to solve for A, B, C, D, but I noticed that the matrix here is invertible. So the easiest way for me to solve for A, B, C, D is to multiply by its inverse. It's kind of messy, but I found if I call 2, 4, 1, 1, B and multiply both sides by B inverse and let Maple do the work, I get that. Now that's very interesting. I have 1 down the diagonal, I have 0 in the bottom left, and I have 2, which is the amount we moved him by, in the upper right. Will that hold generically? Do I just need to put how much I want to move him by in that little spot there? Well, let's look at a generic example. I'm going to say he's at point x1, 1, x2, 1, and I want to move him by d units. So again, getting Maple to do the hard work for me. Oof! Luckily, Maple has a thing called simplified. So yes, if I want to move, oh, these are 2 Ds. Oops. Poor variable planning on Megan's part. Apologies. So if I want to move Bart left or right, I just put the amount I want to move him by in this upper right corner. Now, what if I want to flip him? I know how to flip the entire plane over the y-axis. I just use that, -1, 0, 0, 1. I use one of those matrices we already came up with. But what if I just want to flip him in place? So he's here. I'm going to have to move him to the center and then flip him and then move him back. So let's see how to do that with matrices. First, I'm going to have to move him to the center. So his center is 3 units over, so we move him 3 units to the left. Then I'm going to flip him and then move him back. Now I can multiply that all together and go, okay, I kind of see a pattern here. I've got the -1 here for the flipping, and the 6 is because, well, think about it. If I had flipped him all the way over here, he would now need to go 6 units back to be back where he started from. But typically, we're going to want to remember this set of matrices as opposed to what they look like when they're all multiplied together. Bart the Bug is one-dimensional. What about 2 dimensions? Here is Sparky the Squirrel. He lives on the plane z equals 1 because I'm going to have to do that same embedding thing so I can multiply. His position will always be centered at some a, b, comma 1, and he's currently at position 3, 4, 1, which is his center of mass. I can keep track of several points on his body, so I could keep his position by this because his corners are 2, 5, 4, 5, 4, 3, 2, 3. Just keeping track of the center is not going to help me because if I rotate in, the center is the same. I won't be able to tell. And if he's got a definite left side and a right side, I need more than just 2 points. But technically, I really only need 3 points. If I have like a diagonal and then either the top corner or the left corner, that'll be enough for me to recreate Sparky. I want to be able to multiply him by a 3 by 3 matrix to move him around his world. Since I only really need 3 points to represent Sparky, and I want it to be invertible, I'm going to just use the first 3. Like, what did I have? I have that 2, 5, 4, 5, and 4, 3 are the 3 points I keep track of. And I want to see how I might move him left or right. So I want to move him to 2 plus to this position. So again, using Maple, I crank it out. This is the inverse of that of Sparky, inverse Sparky. Multiply it all out and simplify it so you didn't see the gross part. And sure enough, I have D right here in the upper right corner, and 1's down the diagonal and 0's everywhere else. In fact, the pattern keeps holding. Again, poor choice of variable there, Megan. If I want to move Sparky left or right, I put the amount up here in the upper right. If I want to move him up or down, the amount goes right here. If I want to rotate him, I'm gonna have to pretend he's in the middle again because that's where our rotations are. So he's up on the Z. I say Z equals 1. If I rotate him, I'm really rotating the XY plane, and Z just gets held fixed. So I know Z doesn't change because I'm rotating around it. And I know how to rotate X and Y. I have that weird sine cosine thing that tells me where the new XY points are for the X standard vector and the Y standard vector, and their Z coordinates don't change. So this is how I would rotate Sparky if he was at the center. But if he's not at the center, I need to pull the same trick we pulled before. I need to move him to the center. I need to flip him, rotate him, sorry, and then move him back. And if I multiply that all out, I went ahead and changed X, delta X and delta Y to just X and Y. I get this. I don't want to memorize this. This is way too much. I'd rather just memorize move, rotate, move. This, I can see a pattern here, but it's not worth memorizing. Too much shit I've already memorized. So let's review what we have so far. If I have a one-dimensional object living on the line y equals 1, to move him left or right by x units, I multiply by this matrix with the amount I want to move him up here in the upper right corner. If I want to flip it, I have this diagonal matrix with -1 in the upper left corner. If I want to transform a two-dimensional object, if I want to move them left or right, up or down, I put the amount I want them to move by in the upper right, in the right column. So here and here, first spot, second spot. If I want to rotate them, I have to move them to the center, rotate them, and then move them back. So far, so good, I hope. Oh yeah, everybody's saying it's wonderful. So let's keep going. What about 3 dimensions? Yes, of course we want 3 dimensions because in video games we use 3 dimensions, do we not? So I will have to look at change in X, change in Y, change in Z. It just follows the same pattern. So that's not too hard to see. What gets gross is when you start rotating, because I can rotate around the X-axis or the Y-axis or the Z-axis. I know the Z-axis. Let's look at it in 3 space first. That's how you rotate something in 3 space. We're rotating it around the Z-axis. Z gets held fixed. Their Z coordinates don't change. I need to embed this in 4 space so that when I go to move things left or right, it's actually a linear transformation. So imagine you have a 4th standard vector. It will be 0, 0, 0, 1, and it doesn't change. And the 4th coordinate of all the other guys don't change. So this would be my matrix. Here is the 4th vector, doesn't change, 0, 0, 0, 1, and the 4th dimension coordinate in everybody else's vector stays at 0. So that's how we rotate around the Z-axis. What about the others? Let's look at the X-axis. In the X-axis, that means the standard vector for that slot doesn't change. Neither does the coordinates for the other 2 vectors in that spot. We need to rotate the Y's and the Z's. And they're going to have the same pattern that we had before. I'm using alpha so you realize this is actually a different rotation. We're rotating around a different angle. But X and Y get changed. So now we're rotating using Y and Z. And Y and Z have the same orientation to each other as X and Y. Now I need to embed this in 4 space. Again, the 4th column's not going to change, and the 4th entry for each column's not going to change. And lastly, we want to rotate around the Z-axis. So the Z standard basis doesn't change. Neither does the Z coordinate for the other 2 standard bases. Now we have X and Z interacting with each other in the same way that X and Y did. And then again, I'm going to embed it in 4 space. So I add the 0s and 1s in the corner. So those are the 3 matrices we use for rotating things. So now anybody in space, we move them to the center, we do the rotation we want, and then we move them back. We'll play with this more in class. Hopefully that was clear and not clear as mud. And I think this is a great place to stop.